Hi, I'm Bahar, and I will be presenting statistical optimal fingerprints for the AMOC and SPG. This is part of my recent master's thesis work. First, I will go over some current fingerprints that are commonly used in literature for the AMOC. And then I will describe a statistically motivated fingerprint for the AMOC. And then I will discuss the capabilities of this. So as you know, a fingerprint is a proxy that can indirectly detect the variable when we don't have a long enough time series, which is the case for AMOC, where our direct measurements are about a few decades. The commonly used variables for this are sea surface temperature and sea surface salinity, where there is an average of these parameters taken over large regions of the North Atlantic and South Atlantic. The SPG is also quite relevant in this context, where the sea surface temperatures around the SPG region is also used as a fingerprint for the AMOC. The SPG, subpolar gyre, is a circular ocean current, which is its own separate system. And the relative cooling over this region, over the sea surface temperatures, is consistent with the idea of a weakening AMOC, as it would export heat to the Northern Atlantic, and if it's cooling, perhaps there's a weakening. But the SPG itself has recently been identified as a potential climate tipping element separately from AMOC. Now, the goal of my work is to find a statistically driven optimal fingerprint that can be used in models. And I do this by using regression models. And I want to identify two separate fingerprints, one for the AMOC and the other for the SPG. The idea would be that if it's successful at capturing overall trends, then we can use it for a weakening analysis. And if it can capture variability, then it will be a better idea to use it also for critical slowing down. And these two may also not be the same fingerprint. The result of that is my data firstly comes from 5 different CMAP6 models for the pre-industrial control run and the historical run. I have chosen these 5 models based on the length of the pi control time series and also different ocean models, because the training of my models have been done on the PI control, and the historical run has been unseen by the machine learning model. The data is sea surface temperature, sea surface salinity. I use the overturning mass stream function at 40 degrees north for the AMOC, and the minimum of the barotropic stream function in the North Atlantic for the SPG. And here you have the results. So on my x-axis is time in the testing portion of my pre-industrial control, so the last 20%. On the left side, and on the right is the entire historical time series. And the y-axis is the normalized AMOC strength. So in all the 5 models, or system models that I have used, we have 0.7 plus correlation in all models in both of the runs, and the variability is well captured with a low mean square error. When it comes to the subpolar gyre fingerprint, again, the setup is the same. X-axis is the time in years, and y-axis is the SPG strength. There is more variation within the models, and the correlation is overall 0.4 plus in PI control run. Now, the reason for this was not the focus of my study, but to improve on this, we are planning to work on using mixed layer depth as well for an indicator of the SPG. And also that SPG varies quite a lot within our system models. Now here I compare the traditional fingerprints with the ridge fingerprint that I have just shown on the full PI control time series. X-axis is time. Y-axis is normalized AMOC. On the right-hand side of the y-axis, you have the SSD, because the fingerprints I have used are SSD indices. A perfect graph would map the blue line, the blue bolt line, the decadal rolling mean of the AMOC, one-to-one match with the fingerprint. And as you can see, the correlation is highest for the ridge fingerprint of 0.86. That is the black quoted value. And orange, red, and yellow are the traditional SSD fingerprints, which have around 0.5 correlation. I'm going to also enlarge the red box there so that we can see easily. So that is just that time series. The last bit, the reason I'm doing this is because the rich fingerprint was used just for this section. Setup is the same. And here you have the black line, the true AMOC. The blue line is rich. And the yellow, red, and orange are the SSD fingerprints. So here you can see that ridge is highly correlated and maps variability better. And this is the corresponding graph for the historical fingerprints, where this is taken from one ensemble member of CSM2, where actually the traditional fingerprints have negative correlation with the AMOC, whereas rich is almost having a one-to-one map. Now, when I want to also discuss what else can this fingerprint perhaps do, here on the left-hand side, you see the PI control time series, and on the right, you see historical. My x-axis is correlation with the true AMOC from the model, and y-axis is the correlation with the true SPG in the model. The dots are for different models, the different fingerprints. Again, the color scheme is consistent. So I have blue and purple for ridge, and the red, yellow, orange for the SSD-based fingerprints. In the ideal case, you would see that for the AMOC fingerprint, you would have something along 1, 0. And for the SPG fingerprint, you would have something 0, 1. So it should be clustered to the top and to the right. We can note that for most of the models, the traditional fingerprints are located in more in the middle, where there is not correlation with SPG, and some correlation with the AMOC ranging 0 to 0.5. And for the ridge, it's higher, around 0.75 and more for the ridge for both of them, actually. And on the right, I have the historical time series. Here we have some overlap with within the ridge fingerprints, but also that overlap exists in the traditional fingerprints, where they actually also move a little bit to smaller correlation with the AMOC as well. Now, what else? How else can we test whether this fingerprint is good? On this plot, I have correlation between the true SPG and the true AMOC within the model. And on the y-axis, I have the correlation of the fingerprint AMOC and the fingerprint SPG. Now, here I want to see, one, whether SPG and AMOC are correlated with each other in the model, and two, whether the fingerprint can capture this correlation. And we see that since most of the results are clustered on the positive top right quarter, AMOC and SPG are correlated in the models and scenarios I have used. And since my results mostly lie on the y is equal to x line, the fingerprint is able to capture this relationship in both of these scenarios. The implications that I have for this is that traditional fingerprints are designed for trend, and they're useful for that. But for critical slowing down, perhaps we need different fingerprints. The other thing is, since I have used rich regression and other machine learning methods, we think that these methods are promising and could be utilized. And I guess the more important bit is that the SPG and AMOC perhaps should not be treated as the same system. Limitations are, of course, the regression models are linear in the arguments, so potential for deep learning analysis of these fingerprints. Also, I have only used our system models, not observations yet, so that will be future work. And as I mentioned earlier, I think a better representation of the SPG mixed layer depth could be useful. So in conclusion, I have two separate fingerprints for the AMOC and the SPG motivated statistically from ridge regression, and variability and trends are both captured, so could be used for critical slowing down and weakening. Thank you.